That was easy. That's a whole vlog. Like day one, you just like threw the hardest ones out of the whole chapter on there.
Cash.
Would you agree?
I don't know. I have to look at it and see. Dwayne Lee. Evan Beecham. Thank you. Jacob Bettis. R.J. Darnell. Chad Pryor. Is that thing not following me? There we go. Chad Pryor. Caleb Callison. Hunter Turnage. Colton Mashburn. Dylan Anderson. Dylan Anderson. Chad Pryor. Ryan McGee. Pass this back to him, please. R.J. Darnell. Hunter Turnage. Dwayne Lee. Caleb Callison. Dylan Anderson. Jacob Bettis. Colton Mashburn. Cash Dower. Evan Beecham. Hunter Turnage. Hunter Turnage. James Medlock. James Medlock. All right, well, I've got you here. I can hand back some labs as well. Chad Pryor. Could you pass this back, please? Thank you. Colton Mashburn. Thank you. R.J. Darnell. Jacob Bettis. You. Ryan McGee. Pass that back to him, please. Evan Beecham. You pass that back to him. Dwayne Lee. And Caleb Callison. That's Dwayne Lee. Caleb Callison. Now, on the exam, so who was not expecting the temperature change of the resistance? Why? We went through that and went back through it in class to make sure that everyone understood how to do it. peak voltage. Got a 660 volt RMS AC line. You got an 1800 watt arc welder. How do you get the peak voltage from that? Yeah, you multiply by the square root of 2 over 2. Why do you need to know the wattage of the welder? To find out the current that's in the welder. Now, is there any such thing as peak wattage? The wattage is just naturally going to be the average or the RMS wattage. So you don't find the peak current by dividing the average wattage by the peak voltage or multiplying them or whatever. You have to find the average current from the average wattage that you can then find the peak current from. And there were a couple of you that found the peak value not by multiplying by the square root of 2 over 2, by the square root of 2, but by multiplying by the square root of 2 over 2, or in other words, dividing by the square root of 2, which actually would actually make the peak voltage less than the average voltage, which is not possible. Then we came to the 4 D-cell batteries and finding out the internal resistance. And I even made a point of saying, be sure to show all of your work, including interim steps, just in case you needed a reminder that you're going to have to go through multiple steps to get there. The big mistake that most of you made when you made a mistake on this was you forgot that part of the voltage, that 6 volts that the battery produces, is going to be dropped across the internal resistance, so not all of that 6 volts would be across the resistor. So this one, I actually thought, number 4, I actually thought that was kind of a gimme question. And that one gave more than 1 or 2 of you problems in coming up with 4 possible configurations to get 4 different values of resistance. And in fact, 1 or 2 of you even added some extra resistors. One of you did it with 4 resistors for the last couple of examples. This, just for the record, here are the 4 possible configurations. 3 resistors in series. 3 resistors in parallel. 2 resistors in series in parallel with 1 resistor. And finally, 2 resistors in parallel in series with 1 resistor. And at that point, calculating the total resistance is the sum of the 3, the reciprocal of the sum of the reciprocal, the sum of the 2 in parallel with the 1, so, and then the 2 in parallel added in series with 1. And the final one. It was important to understand that when you close that switch, what's going to happen? when you initially close the switch, the current is going to start to flow and charge the capacitor. As the capacitor charges, the voltage across the capacitor will increase. The balance of the voltage will be dropped across the resistor. Once all of the voltage is dropped across the capacitor, the voltage dropped across the resistor is 0 and the current flowing is 0. There's no more current flowing once the capacitor is charged. This is not the same as when you discharge a capacitor. When you discharge a capacitor starts with a voltage already developed across it, and it generates current until the voltage across the capacitor drops to 0. How does the voltage across the capacitor increase? The voltage applied times, anybody? Right. That's the equation that you're working with. Remember, at t equals 0, e to the minus 0 is what? 1. So 1 minus 1 is 0 times the voltage applied. So you at t0, you have 0 voltage across your capacitor. If you eliminate this 1 minus and just plot directly e to the minus t, now you're talking about a discharge, because it starts off at t equals 0 at 1, and as t increases, it gets smaller. Is there anyone here who doesn't understand how this one was then solved? Is what were we asking for? Yeah, in fact, if you'll notice, I even wrote, assuming the capacitor starts at V sub naught equals 0 volts. And we're looking for how long does it take the voltage across the capacitor to reach 7.5 volts. So from 0 to 7.5. Well, then you're setting up 7.5 volts equals V sub naught is, you're applying 10 volts to the circuit. So that will reach 7.5 volts when what's 7.5 volts divided by 10? When 1 minus e to the minus t over RC is equal to 0.75 volts. Subtract 1 from both sides and you get does anyone not know how to solve that now? Take the natural log of both sides. The natural log of minus E is minus T over RC. Or is that plus? and then you solve for, you know what R and C, you know RC, so you solve for T. Came out to 1.39 seconds or 1.4 seconds. I'm sorry, 0.14 seconds or 0.139 seconds. But it did require that you first set up the problem correctly. So, now, does anyone have any questions about any of the exam problems? There is one thing that I do want to point out to y'all. I want to emphasize this. At right now, when you go to Canvas and you look at your grade, your total grade in the class is reflection of the work that you have done. Okay? It does not reflect any of the work you have not done. Okay? So now that means it can be a little bit misleading, because if you have assignments that you didn't do that are, they're 7 points apiece. At some point, I'm going to have to say, okay, this is the end of the deadline is this week. You need to have everything turned in that's overdue. Okay? At that point, any of those homework assignments that you did not turn in are going to turn into zeros. And that's when that will really hurt your grade if you're missing them. Okay? More so than homework assignments, any labs that you have not done, that you missed, those labs, when they turn into zeros, they're really going to hurt your grades. Okay, so get on Canvas. Find out what assignments and what labs you're missing, and turn them and get them done. I want to give you every opportunity to get all of them done. Okay, but I still have to grade them. And the end of the semester hits, I don't get any grace period to turn in your grades. I have to turn in your grades by the deadline. And I can't wait until the last few days or the last couple of weeks and have, a 2-foot tall stack of papers that still have to be graded. So, you're asking what can you do to improve your grade? That's the first and most efficient thing you can do, is find out what you haven't done and what you haven't turned in yet, and get it done and get it turned in. Get the points. And again, I encourage you to work together on these homework assignments. Help each other. Figure out, go through it, because I guarantee you, two sets of eyes are always better than one, because you don't know when you miss something. It's like you read the question. If you misread it, you don't have any way of knowing that you just misread it. So if you've got someone else reading it alongside of you, they might catch it.
I didn't have much trouble with any of the homework for the past chapter, but I really feel like you put the hardest problems out of the homework on. Some of these were just little Kirchhoffs, solving for power, easy stuff like Ohm's law. But then you just put the temperatures on there, and the time. We had one problem on the homework that was those. And that was the one that I struggled with.
Okay.
I don't know. I just feel like there was a lot of easy stuff on the chapter, but you put the harder stuff.
The easy stuff is intended to prepare you to be able to do the harder stuff. If you'll notice in the homework assignments, they always start off with dirt simple problems that build to more and more complex problems. And while I do try to test you for the material that we're supposed to have learned in this chapter, not just the easy stuff that you learned 2 years ago. At the same time, I also very much try to make these problems as easy to work as they can be. Okay, it's not like you had to solve a system of equations to come up with any of these answers. Now, when it does get tricky, I also try to give you clues, like be sure to show all of the interim steps, telling you there are interim steps. You can't just plug in the numbers to one equation and get an answer out. All right? Now, all of that said, I still have to point out to you that as a class, you're all in good standing right now to pass. Yeah. Sure you are. Why aren't you? Well, if you're shooting for a 4.0, then you're up a creek. Okay. I don't want to discuss anyone's particular grades in front of everybody.
I don't care to discuss mine.
Well, then.
It was looking good, and then this freaking test.
Well, then let's get with me after class, and we'll sit down and look and see where the problem is. Well, okay. Y'all get all of your past due homework and past due labs done and completed. And if y'all get them done and completed in time, and there's still a few weeks left to do so, then I will look at doing a bonus or a makeup test and putting together a makeup or a bonus exam that can go in and replace a low grade. And you're right, I'm already dropping the lowest grade. Okay? I'm not going to drop all of your low grades. Okay? That onus is on you to make some higher grades. Okay? But I'm also not trying to fail anybody. I want you to learn the material. I want you to be able to look at the problem and know, okay, this is what I need to do to get to that answer. Okay? I also want you to know what you don't need to do. Okay? Because that's the trouble with algebra is most of your time you spend learning algebra, you spend chasing rabbits down wrong trails. You know, trying one approach and getting to the end of it and realizing, oh, nope, that's not going to work, and having to start over again. Learn to look for the clues in the questions. That will help a lot. But no, I am not going to give you a test. I'm not going to give you a 120-point test in an upper-level physics course that is nothing more than finding out how well you can manipulate Ohm's law.
That's what I see. Like, you look at this homework assignment, it's pretty easy stuff. Then you get to 36, which is the time one. That's the hardest one on the homework, and that's what's still on the test.
Okay.
I mean, I'm not trying to tell you how to make the test.
Well, maybe a little bit. You're trying to tell me how you would like them made.
Oh, yeah, I'll tell you how I like it. We do more harder, like, questions, like what he's saying in class, so we, like, all know what we're doing.
I have, and I will, and again, this is yes. The short answer is absolutely. And how many times do I get up here and basically beg y'all for any questions from the homework? Is there anything you don't understand? Anything you want to go over? That's why. You mean like right now? Sure, I can make something up off the top of my head. Yeah, do the homework. Do the homework. Get all of your homeworks done and turned in. Because I'm begging you. I do not want the end of this semester to roll up and then have you have to look at a bunch of zeros pop up in your grades. Get on Canvas, find out what homework assignments you haven't done, do them and turn them in. Find out what labs you missed. You want quizzes, you want points to build up your grade? Missed labs are 22 points apiece. That's 3 homework assignments plus 1. Those are definitely going to, if you're missing labs and at the deadline and those zeros hit, that is definitely going to hurt. Get those done. And if there's still time, then yes, I will put together a bonus exam. That's something that we can do in class, and it will replace a lower grade on one of your lower grade exam grades. Okay? But it ain't going to be manipulating Ohm's law. Okay? Yeah, well, it's what you're here to learn. And you're here to learn more than the Ohm's law that you learned 2 years ago or 2 semesters ago.
Right. I would only accept the Ohm's law on there. That would not be.
Yeah.
That wouldn't be right. I just feel like it's just the hardest one.
This one right here.
I mean, yeah, that
This one, I could not believe that anybody lost even a point on this question.
I mean, you did put.
I actually, if you really recall, I actually went through a whole lecture period. I don't know if it was a whole lecture period, but I went through and derived from scratch how and why this is a sum and this is a reciprocal of the sum of the reciprocals.
I believe.
And, because I know you've already learned how to add resistors and, and how to make the combinations, and the same with capacitors. But I don't know that you ever learned why. And that's the difference between this class and Electronics 101. So, you are in an upper level physics course now. It may not be calculus based, but it is an upper level physics course. And when you finish it and you pass it, you may not have a 4.0, and you may not even be able to go back and do any of the stuff that you learned how to do just off the top of your head. But when you do find yourself working for the power company or for the airplane part manufacturer or wherever you end up working, and some of this stuff comes up, you are going to know where to go and look up the answers to figure out how to do the problem, how to solve the issue. Okay, that's why I tell y'all to write down stuff on these index cards. I'm not trying to make you memorize a lot of stuff that you don't need to know, that you're not going to need to use after you finish. But I do want you to be able to figure out how to look up what you need to know and how to use it correctly. Yeah. Well, that's half the class. Do we have any more questions? Have anyone started the homework from the week 9 that we're in now? Or has anyone got any questions from week 8?
Can you do number 26? I got kind of confused on that. I looked it up, and I have an answer, but I don't know.
Number 26. If an electric wire is allowed to produce a magnetic field no larger than that of the Earth, at a distance of 12 centimeters from the wire, what is the maximum current the wire can carry? Okay, good problem. Let's... Oh, good night. No. Where's the trash? Here, find a trash can for that. Oh, that is not even going to work. Oh, look at that. Oh, and for the record, ain't nobody ever looked at me and thought, man, I bet he can play basketball. Oh, don't worry about that. I'll get that later.
Oh, that would be other blue ball. Hey, not that. You want some water?
No, this is fine. I'll clean it up later. It's the best way to clean up. See, when you write on it with the other markers, it goes away. Yep. Well, I'll just have to draw darker. Oh, and by the way, if you ever have a whiteboard that somebody uses an actual marks-a-lot on, a magic marker, you want to get rid of it, just get the black dry erase marker, rub on it with it, wipes right off. Okay, what are we looking at? 26, electric wire. First of all, what is the magnitude, what is the Earth's magnetic field? Generally speaking, the B field, the magnetic field of the Earth is going to be about 5 times 10 to the minus 5 Tesla, which is equal to about a half a Gauss. Not that we're ever going to use Gauss. But if you'll recall, a Gauss is 1 Tesla is 10,000 Gauss, or 1 times 10 to the minus, 1 times 10 to the 4 Gauss. So a Gauss is 1 times 10 to the minus 4 Tesla. And the Earth's magnetic field is about half of that, or 5 times 10 to the minus 5, or 0.5 times 10 to the minus 4. Okay, now we need to know the equation that describes the magnetic field produced by a current in a wire. Anybody remember that equation? There's the force on a current in a wire or a charge in a field. I also want to talk about the Hall effect with y'all if we get a chance. If you want to see the equation, it's on page 570, equation 20-6. The magnetic field produced by a long straight wire is equal to mu sub naught over 2 pi times the current divided by the distance, the radius, or the distance from the wire. Make sure I wrote that right. Yep. Now, if you'll recall, that was one of the right-hand rules of thumb. You've got a wire, you have a current flowing through it. Point your thumb in the direction of the current, close your fingers around the wire, and that shows you the direction of the magnetic field. In this case, with the current going from the bottom to the top, the current flowing upwards, magnetic field wraps around behind the wire, comes back out and back around in front of it. Or it spins counterclockwise, looking from the top down. The magnetic field around a wire is always going to be concentrically circular. So the magnetic field is, at this point, is that radius away from the wire. Okay? Now, in this case, the problem is saying if you have to restrict the magnetic field that wire is allowed to produce to no more than the magnetic field of the Earth, what you're saying is what current will produce that magnetic field. So let's fill in the equation. 5 times 10 to the minus 5 Tesla is equal to mu sub naught over 2 pi times some unknown current divided by the radius of 12 centimeters or 0.12 meters. Does anyone remember what mu sub naught is? Permeability of free space. Beautiful. 4 pi times 10 to the minus 7. Is it minus 7? Should be minus 7, right? Somebody confirm that. All right. So, what's mu sub naught divided by 2 pi? Pi's cancel. 4 divided by 2 gets 2 times 10 to the minus 7. So, we got 5 times 10 to the minus 5 is equal to 2 times 10 to the minus 7 divided by 0.12 meters times our unknown current. Solve for I, we get 0.12 times 5 times 10 to the minus 5 divided by 2 times 10 to the minus 7 equals I equals, somebody with a calculator do the arithmetic, please. $30 amps. Is that the answer you'd gotten? Let's take a minute here and talk about this a bit. Because this is a subject where it's very easy to confuse yourself by overthinking things. In this case, we were talking about the magnetic field that is produced by an electric current in a wire. We are also looking at, in other examples in this book, we also talk about the force that a magnetic field would exert on the current in that wire. Okay, and that's not the same thing. This is the magnetic field produced by a current. B equals mu sub naught over 2 pi times the current divided by the radius or the distance from the wire. Remember, it's a long straight wire that we're dealing with, the long straight wire. So the magnetic field it produces is always going to be circular. And so it's natural to talk about the magnetic field at a radius from that wire. Now, we also talk about the force that a magnetic field exerts on a current. The force a magnetic field exerts on a current on an electrical current of so many amps. And that force is I times L times B. The current times the length of wire that is exposed times the magnetic field that is perpendicular to the wire, or the perpendicular component. So we write that as a sine of theta. Here is another place where you need to think through what's going on. They draw this magnetic field, and they draw the wire passing through it. So here is your length. Okay? What is the perpendicular component of that magnetic field? And what's the parallel component of that magnetic field? If this is the magnetic field, what angle are we working with there? Well, this would be the perpendicular, the 90-degree component of this vector. Okay? When would this angle be 90 degrees? That would be 90 degrees. That would be 0 degrees. At 0 degrees, the sine of theta is 0. When the wire is parallel to the magnetic fields of line, the force it exerts is 0. When the wire is at 90 degrees, the sine of 90 degrees is 1. So at that point, the force exerted on the wire will be the maximum force that B field can produce, the full B field. At this angle theta, it's going to be the B field times the sine of theta. But there is a problem in your homework where it talks about a coil of wire with 9 loops that's got the magnetic field is passing through it at minus 57 degrees below the horizon. Let's look at that problem. Here's your coil of wires. Remember we talked about how when the square loop of wire goes through is in the magnetic field, that the magnetic field is going to produce a torque because of the force on those 2 wires going around it? Well, same problem here. And we're going to look at that and see how that derives. But in this case, they've got the coil of wires laying flat on the ground, and the magnetic field, the Earth's magnetic field, going 57 degrees below the horizontal, pointing into the ground. And they ask for the torque that this field, that this magnet, that this would produce on the current flowing through that coil of wires. We're not going to worry about the equation of the coil of wires and how to find the magnitude of the torque, but just to analyze the angle that you have to work with here. When would the torque be maximum? when the magnetic field is perpendicular to the face of the coil. That's 90 degrees here. When the coil is like this, then the torque is 0. So the point is, make certain that you're using the right angle between the field and the plane of the wire or the plane of the coil or whatever you're working with. Okay? And if you let it, it can and will confuse you. Now, if that's 0 degrees, that's 90 degrees, and there's your 57 degrees. Well, we're talking about the magnetic field produced by a current in a wire and the force that a magnetic field will exert on the current in a wire or on a charged particle moving through a magnetic field, like an electron or a proton. What if... Now, I'm writing this out for you for a reason. If we're talking about a force exerted on a moving charged particle, then that force becomes Q times the velocity times B sine theta. Instead of current times length, you have charge times velocity. That's the only thing that changes. Here you have coulombs per second times meters. Not Q, C. What do you have here? Coulombs times meters per second. Okay? This and this are equivalent. They're functionally the same in the equation. It's the same force. It's just in a wire, it's how much charge per unit time is moving through that distance. And for a single charged particle moving in a field, it's that charged particle times its velocity. I showed y'all last time about how you get the cyclotron equation by setting this force equal to setting up a uniform magnetic field that's everywhere perpendicular, so you get rid of sine theta. And then setting that velocity equal to the centripetal acceleration of v squared over r. And that gives you the force is equal to the centripetal acceleration of, well, it'd be mass times v squared over r. would be the force. Okay? And that's how you then solve for the perfect circular motion of a charged particle in a magnetic field. Given a given radius, the velocity you would have to have. Is this? Okay, let's do this one in review then. We've got a magnetic field that is uniform and a charged particle moving in it. That charged particle will move in a perfect circle when the force exerted on it by that magnetic field is centripetal. Okay? But we know the force that the magnetic field produces on that charged particle will always be QV times B. Did I get that right? Yeah. Because the field is everywhere perpendicular. It's uniform, it's always perpendicular. So sine theta is always equal to 1. And that is, so when we set that equal to V squared, mv squared over R, we can solve for which one do we not know. The problem may tell you in this strong of a magnetic field, what velocity does the particle have to move in a circle of this radius? Or it may say the particle has this velocity and is moving in a circle of this radius. How strong does the magnetic field have to be? This is what you're solving to find that out. Okay? Yeah. That is centripetal force. The centripetal acceleration, that's from Physics 1, perfect. That's mass. Yeah, that's... Okay, because remember we're dealing with forces, so it's the mass of the particle times the centripetal acceleration is the centripetal force. And that's what you have to set equal to the force that the magnetic field exerts on the particle. And at that point, whichever one of these variables they're asking you for, you should be able to solve for. Okay? Sine theta equals 1 because in a cyclotron you will set up two big you'll set up a big magnetic field that is everywhere uniform. So when the charged particle is moving in that magnetic field, the magnetic field is always at 90 degrees to the motion of the particle. And so the sine of 90 degrees is 1. Yeah, this would be, the magnetic field would look like this. Everywhere, over an area much greater than the circle that it's moving in. Now, was there something, I feel like there was something I was trying to address that I didn't get to. I know there's a lot I didn't get to. Hall effect is one, yeah, but was there another question that had been asked that I got sidetracked on and did not answer? Yeah, okay. Well, I will see you on Wednesday. I'll see you tomorrow for lab, yeah. And I'll see you again on Wednesday. If you have any questions on the homework, we can address them tomorrow too. Great. Thank you. Yes, please.
Well, they're not even reflective on it.
Yeah, they're not added. They're not helping his grade. They're also not hurting it because they're not being put in as zeros. Yeah. You have. Okay. Then what? At this point, the next step will be to get let's see if we can get a bonus exam or something that we can add. We can go in and replace one of the lower scores. So let's work on that. But what's your name? Jacob. Jacob Bettis? I don't really